So if there is an anomaly, every time when there is gamma phi, then of course there will be gauge anomalies. And remember what I said, I could view the anomaly as this triangle, imagining a current here and two gauge bosons here. Any gauge boson. I can also imagine then, obviously, there is a current associated with the gauge boson also, therefore I can imagine diagrams like this. And they relate to anomaly in general. Why? Because they're weak interactions, for sure. Without weak interactions, no. You need gamma phi, right? If you think of QED or QCD, every time you have gamma phi on the left, you have gamma phi on the right. So there is no gamma phi, right? The coupling with the photon is of this type. There's no gamma phi, which is to say that there is both left and there is right. But the weak interactions, why are they? Every time there is a gauge boson, there will be associate generator at the vertex, right? And I have to take a trace of this diagram. And so there will be terms and all possible permutations. But the trace is cyclically invariant, therefore this is proportional, all of this, to trace Ti, Tj, Tk. You can convince yourself as I'm speaking. Just take any other combination, you will see by cyclicity you will bring it there. And if any theory, gauge theory, is to be normalizable, the anomaly must vanish. Because we said, what does the anomaly mean? Whenever there is, so this is okay, this I don't have to worry about, but I have to worry about AMU3. Before, AMU3 would couple in the standard model, but T3 picks up left-handed fermions, right? This is the, for example, or any Ti. Every time I have a non-vanishing T, I have a left-handed fermion also, because by definition, Ti acting on right-handed fermions is 0 in SU2. That's why it's called left. And that means that whatever piece has gamma phi, the current won't be conserved. But you use the current conservation in QED. Remember how I used it to get the Warden additive. With that Warden additive, you could show, I don't know, that Z1 is equal to Z2. Remember when you were a normalizing child? That was fundamental. The great success of gauge series is precisely in preserving gauge invariance, and then there was, remember the whole point about the standard model was this thing that Hoff realized, the spontaneously broken gauge symmetry. It's sort of hidden, as Coleman used to say. It's not really broken, it's there. So that means that this must be 0 in any renormalizable gauge series. If and only if it is 0, the theory will work. So let's see what indicates for the standard model.
What do you mean by anomalous? Is it like for example, for case of electron QED, like Barber moment, or like interaction electron with photon, but here you can see interaction goes with itself?
This is what I mean by anomaly. The current is not conserved. when there is gamma phi in such a vertex, the associated current won't be preserved.
So current conservation is critical for world identities. That's why.
Yes.
And in this case, we calculated this diagram. Do we expect this to be zero or momentum times this to be zero?
Yeah, you will take the derivative, you will do whatever you do. I don't now worry about computing it. I'm told that the anomaly is there. Who cares? You and I don't care. Someone's taught us, after all, I didn't teach this. I just said take it for granted that the axial current is not conserved, but it has to be conserved. And even if by taking the derivative of the proper current I get non-zero, if this vanishes, then I will get zero.
Okay, what is...
In other words, the individual diagram will not vanish, but the sum of the diagrams may vanish.
I'm asking that if we impose to be zero, do we impose something stronger? Or is it enough to say that derivative vanishes? Condition is enough to say for diagram?
Yes. When the currents are conserved, this is all that you used. When I speak of gauge invariance, what I mean actually, I mean first the global invariance. The currents are conserved because of the global invariance. Gauge symmetry, it's not even a correct language. It's this redundancy of the degrees of freedom that we use. But it's all based on charge conservation, if you wish. Charge must be conserved. Once charge is not conserved, you don't know how to formulate. Actually, there were even more serious problems that I want to dwell on, okay? But certainly the way you have taught, it was crucial that the charge was conserved. So I don't know who taught you the course. He or she should have emphasized this in a very physical manner, that if charge is not conserved, you will see that the theory doesn't exist. This is why I will always insist that, for example, in the case of gauge series, when you need charge conservation, then that point of zero is a special point. You can't move a little bit. You cannot say, oh, maybe conservation of charge is violated a little bit in QED. Even if you say that the charge of neutrino, that would imply, for example, that the charge of neutrino is not zero. Even if it's 10 to the minus 50, the theory won't work. You won't be able to compute anything. So by definition, remember, QED is that theory that we use perturbative in order to compute. It's not the Lagrangian to write. That's very important. Lagrangian is the zeroth point, not even first point. Then you go and compute perturbatively based on some well-defined rules. Okay, those perturbative calculations are based on charge conservation. That in particular, and remember that was fundamental. When you did this, did you pay attention that there were diagrams like this? If these diagrams were not to cancel, there would be no sense of speaking of the values of charge. How could you keep charge quantization, this incredible thing? One charge will renormalize differently. You see, if these give zero, which they do, then the charge renormalization comes from here, which treats everybody equally, okay? Whoever you are renormalizing gets renormalized equally. Therefore, that's why if I tell you that the charge of the electron is 3 times charge of the downpore, it stays 3 to all of this perturbation theory. Otherwise, it will be immediately violated. You see, if this charge was a third of, so in one case I would have third, but then it will become 1 over 27, you know, at one loop and then the next loop, okay? So. I won't go on, just feel free to keep asking. This we should do as informal and sort of, because again touches to the basics.
Why should cancel? What's wrong with the normalization here with the charge?
If the charge is not conserved, there is no theory, QED. You never studied it, it doesn't exist. The whole thing that you did last semester, okay, I don't know how to help you with the another yes statement, was based on charge conservation.
Yeah, but the diagram, like if I consider instead of an electron, consider a quark, what will make different for the quark than the electron? This diagram.
Oh, here? Well, it suppose there's a cube of the charge.
Okay, so.
Take some charge Q.
Yes, in the vertex.
These diagonal boys Q.
But we have also.
So Q will be 1 plus order alpha QQ. How to say Q0? Let's say something like this, right? Okay. This is not renormalized linearly.
But also that diagram.
Q prime would be. No, what do you mean this one? This one is proportional to. There is just one charge.
But also in the floating propagator, there also.
No, these are summing all this. No, here everybody contributes. This is some number.
Okay.
No, this is some number, but this is proportional to Q0.
Okay. So there we put every value in the.
Yeah, this is alpha times Q0.
Yes.
Times, of course, there is a number C. I'm isolating, there is also here some number that I don't write, but it goes as Q0Q. Here it goes as Q0. Every charge will be equally renormalized because everybody should contribute. Even if you take an electron and not a core, you must sum all the fermions here. Remember, here there is a sum of all the fermionic contributions. QF squared and whatever else contributes, okay. So it goes linearly, which is nice. So for example, here you would write that Q is Q0, 1 plus. So whatever was Q0 would remain proportional to Q0. And Q prime would be Q0 prime with the same coefficient. Exactly. Okay, this is what is essential in this diagram. This formal thing, I don't know if you got lost in this word identity without seeing what's going on. It seems to me the way you are looking at me, okay, this was crucial. This was based on the conservation of current. Ward derives Z1 equals Z2. Because look, I can show it at one loop. I'm not going to show it at 37 loops. Okay, how in the world would I do that? But you can show it at all the perturbation theory that these diagrams cancels. For example, among other things, the conservation of currents give you that. So look what you have. That Q prime over Q is Q0 prime over Q0. So the magic of charge ratio stays. I don't know why that magic is there. And today we'll discuss possible answers to that. So finally we discuss maybe the nicest aspect of modern particle physics, or not so modern particle physics. I would say the most beautiful topic, without doubt. And that is the understanding the quantization of charge. I'm not saying that I understand it at this point, but all I'm saying, whatever it is, it will remain preserved to all orders in perturbation theory. You can now address this to all orders. I don't care what you do here. There will always be some number which we treat all the fermions equally. What is important that all other contributions vanish. Okay, I'm giving you one example where the conservation of current is crucial for formulation of QED. So in particular, this is not zero, but it must be zero for normalizable if this is a gauge current. It doesn't matter if it's some global current like baryon number or so on. Okay, so maybe baryon number is broken, or lepton number, or whatever the global symmetries you can imagine, but the gauge symmetries, no. And this is a distinction I was arguing now for 2 days. And it's not somehow working because yesterday both Michael and Nicolas were saying, oh, but symmetry is something special when it's zero, and I insist there is nothing special when a global symmetry is exact. Nothing. Gauge, yes. That's very important to comprehend this difference. What you do with it is another story. In a gauge case, I have to live with conserved current. I have to be in the exact gauge symmetries are exact. Of course, they can be spontaneously broken. There is this miracle that spontaneous breaking is not breaking for.
Yes, like for those symmetries that can be spontaneously broken, then they become important.
Well, they can be spontaneously broken, but again, in order to speak of them spontaneously broken, you have to tell me, are they just spontaneously broken? Or mostly spontaneously broken, to argue that the explicit breaking must be zero, which it's there, 10 to the minus 20 is as good as zero. I don't know how to quantify that. Here I know. You have this cannot be a little bit. You cannot have a little coefficient here.
How about the explicit symmetry breaking brings some mass to the Goldstone bosons, right?
Precisely. That will be a way to knowing. For example, there is a way of measuring. Okay, and if the time permits, when we speak about the axion, this will be interesting. The trouble with the axion that it's not a completely Goldstone boson. You know, it's like a pion. But a nice example is a pion. Pion. Okay, let me not speak at the moment. I'll come to the pion a little later. What I wanted to graph here is, now that I ask you to accept the anomaly, to show you the magic of the standard model, the extraordinary magic. In the standard model, this does vanish. But how it vanishes, notice. For example, what are the generators? I have Ti, I equal 1, 2, 3. Now let me, TA. I goes over all, whatever is the gauge group, I is all. And then we have, let's say, T4 is hypercharge in the standard model, right? These are the important chiral charges, chiral generators. The others are not. So, for example, one thing that has to vanish is trace TATB hypercharge. I cannot take anything. But this is 1, right? This is delta AB. The standard model, now you should be excited, we are checking a miracle. And that has to do with the charge quantization, okay? In the standard model, this must vanish. So trace of what, which is, remember, trace of 2 times trace Q minus T3 must be 0.
And is the anti-commutator?
Sorry? This is an anti-commutator here. Oh, of course.
Yeah, okay.
Not a commutator, no, they're all equally contributing. All the perturbations, all the permutations contribute equally, of course. There is a symmetry here. If I want to compute this diagram, I'll take all the possible contributions here.
Why did it say this term is 0 when we just put y, not other possibilities?
I'm starting. You can think while I'm doing it why I started with this one, because this one is more striking, okay?
Okay, but we will be satisfied. The sum is.
Oh, I could have written trace TA, TB, TC, but you know that this is 0 in SU2. Okay, let me start from here. This is trivial. Now A is SU2. Because they're traceless. And they okay. I want you now to be familiar with SU2. I don't have to say this. This you have to, now this is not April or May, okay? Now you're masters of you're going beyond the summer, you're in the summer school. You will know forever SU2, okay? This you will remember how much I was telling you about SU2. Okay? You see quickly that this is 0, okay? Any combination.
So we need to choose at least one outside of SU2, so we need to put somewhere y to make it non-zero, right?
You have to do everything. The rule says that you have to go over the whole gauge group and see what vanishes, what not vanishes. Something will vanish trivially. Well, I will now tell you go on and check it, but at least let me show you something, okay? To this day I'm excited when I think of this. When I first time realized, and people debate now the importance of this. Trace of T3 is 0, the generator traces, so this is proportional to trace Q, and this better be 0. And lo and behold, look at the left-handed guy, because it must be true for left-handed guys. I had here T8s, which are not vanishing. If I look at the right-handed guys, this will be 0. So let me be clear here. This is picking up YL, notice, which is QL. That's important. It has to happen in the left-handed sector here. Otherwise, TA is a 0, okay, so then it's trivial. Nu EL and UDL. So what do I get here? Trace of QL is -1. Together, we have to do this together. Trace of QL here, so lepton quark is, say it loudly please, 2/3 minus 1/3. Another proof of 3 color. Without 3 colors, this miracle would happen. This is +1. So let's be precise here. Let's do something else here. Let's do it the other way around. Let me write UDL. I will write the charge of the up quark is 1/2 plus charge of the down quark. No. Yes. No. No. I wrote something stupid, but help me. I need some lively energy. Q in a doublet is T3 plus something that I call hypercharge. That means the delta Q, hypercharge of course by definition must be the same in they commute, the hypercharge in SU2. So delta Q in a doublet is 2T3. So maybe I better put 1. Q of the up quark, I don't know what the Q of the down quark. Let me now not know what the up, let me forget that proton is made of 2 up quark and so on. Now I'm given some quark picture, people tell me I want to formulate the standard model in which I have a leptonic doublet and a quark doublet, but I don't know quark charges. So you say that trace QQ on the left-handed side is equal to Q up plus Q down, you agree? By definition. And that's 1 plus 2 Q down. I don't like what I got. Maybe I got some methods. No. Yes. Maybe it's okay. Well, maybe it should be times 3. Sorry. Sorry.
The color included in the Q. Like you have QU, but you have 3 times QU.
So I should multiply by 3.
It's plus and another one's minus.
Is this correct? Let's go step by step. Correct? Seems correct, right? Let's go home.
I think in our formula, we're already multiplying each one by 3.
No, -1/3 plus 1 is 2/3.
Yeah.
So it is.
No, here I have not multiplied anything. This is just the SU2. When 2 guys in a doublet, notice the neutrino has a charge which is 1 plus the charge of the electron. This will be true for any species.
Okay.
That's for sure. The upper guy had charge.
So what we assume this doublet has a color index also. Multiply by 3.
Of course. Of course. No, I'm in the same picture, but I don't know what the charge of the down quark is. Normally what will happen, if I live in a non-mysterious world, the charge of the down quark will be some arbitrary number. This, you know, here there is nothing of integers. I just call this 1. Okay, it's not that this is 1. I just called it 1. Then you will say, you know, if his weight is 1, my weight is not going to be 1/3 or 3 times. I'm sure we can put a scale to the precision in 1 in 10 to the 20. Okay, you will notice that with some random factor, we should throw together on the scale to appreciate the drama of charges, okay? So I should get 1 plus 2 QD times 3. And that must be equal to plus 1, right? I don't like it.
Oh no, it's okay. It will give minus 1 over.
It will work. You see why I was late? It's sort of embarrassing. I make sure I don't teach in the morning so I'm awake. But I fell asleep. I somehow was working, I got up very late. I fell asleep. I barely managed to wake up and come here. I even put the alarm because I didn't dream that I would fall asleep. I'm still waking up. So you guys have to help me. Okay? Today we work together. I have some notes, but we can try the thing. Normally I don't look at the notes because I'm prepared. So this is 3 plus 6 QD is equal to 1. Must be equal to 1, let's be precise. In order for anomaly to disappear, in order for the consistent, normalizable standard model gauge theory. So what do I get? That 6 QD is minus 2. QD, it was faster than me, it's minus a third. I have predicted the charge. Standard model predicts charge quantization. Many people will say this. This is a delicate question. It predicts in the following sense. It predicts not because of some deep structure. It predicts from a necessity to be able to do perturbative calculations. Therefore, you see, it predicts it from our ignorance to work with the theories when this doesn't happen, but it's interesting that the prediction is there. The charge of the down quark must be 1/3. This is charge quantization, by the way. Once you have this, you have everything else.
The first one, we choose the charge of the first of the electron, mu to the neutrino atom. That is an arbitrary.
No, that's a definition of electron charge.
That's a definition. An arbitrary
That's
charge.
just the one.
Yeah.
No, I normalize.
Okay.
It's less choosing your weight. That's a kilogram, what I call. No, that's.
So that's the standard. I mean, we call it our
Yeah, this is.
such that we.
Well, the charge quantization is that the ratio of the electron to down quark charge is 3. Doesn't matter what you
Okay,
call.
okay.
I could have done better. I could have written QE there, you would have seen. Good, I should have done that to show you. And you would find out that QD is minus a third of QE.
Because at the beginning we started saying that hypercharge is kind of an arbitrary thing.
Yeah, sure, but at the
now
end
we
it's
show
not.
that
Now we show that it cannot be
it's
arbitrary.
not arbitrary.
In order to discuss that, you need the anomaly. So I said I can't talk about it. There is something. There is some. I mentioned it en passant. You probably don't remember. I said there is something here deep. Okay. Now, two things. First, it doesn't predict charge quantization of all particles in the world. It predicts the charge quantization of the families. For example, I can immediately add a fermion. Let me add a new fermion FL and FR, which is a singlet. Notice it's a singlet, both left and right, and the charge of this guy can be epsilon, because the anomaly will cancel between left and right. Here, it cannot cancel between left and right, because only left will have this TATB. Okay? So remember, if there is no difference between left and right, then of course there is no anomaly, because there is no gamma phi. So in order to have an anomaly, you need a difference between left and right. But if I introduce a set of particles in which left and right, and we don't know that these particles don't exist, their masses could be very large, okay? In other words, standard model does not guarantee that all charges are quantized. It does something special though. It guarantees charge quantization between our quarks that make you and me and the electron that completes us.
So only the particles that feel the weak interaction will be like charge quantizing this way. This is that.
Sure, well, not necessarily. I can add a doublet now. Not necessarily. I said this is a singlet, take it a doublet. Again, the charge can be arbitrary. As long as the left is equal to right, the anomaly cancels automatically because there is no difference in this world. And this is this is a picture that you and I would have imagined. Remember the excitement that when people learn that left is different from right, these two guys, I show you the pictures, or did I? Li and Yang looked your age. And they were almost your age when they got the Nobel Prize. Because you never expected somehow that the left would be so different from right. Okay, unfortunately, even any representation of SU2 would automatically cancel anomaly if left is equal to right. Make it a triplet, quintuplet, whatever. And you know, anyway, SU2 has no anomaly. SU2 has no anomaly. Trace T, A, T, B, T, C, 0. You've seen that these are Pauli matrices. This is 0. Okay, that's very important.
Can we add a left-handed and right-handed doublet for SU2?
Yes. Yes.
But we should not use the Higgs mechanism as we use.
If you would use the C, yeah, no, because the Higgs will not give them. They have actually automatically mass. In this world, there will be no Higgs mechanism. If left was equal to right, then all this magic of...
I mean, there are the standard model particles with singlets, right representations.
No, doesn't matter with singlets or whatever. This is invariant. For any representation, as long as they are the same, this is invariant. Doublet, triplet, quintet, 70plet, okay? The only way the only way to have Higgs is to split left and right. So the magic of the standard model, everything that you see is because of the asymmetry. And that is why it's worth reading if you're interested in the beautiful essay by Weinberg, V minus A was the key. V minus A established that the world is completely left-right symmetric, that only left-handed current participate in Fermi theory. So they went on and constructed the standard model. Now please complete it. You could do it if you think a little bit without my help. You may need my help, but I want you to go home and check it. That everything else will give you, that I've actually checked everything. In principle, you can tell me, well, you can take, what could I have forgotten? Maybe twice hypercharge. Okay, check that if you're not convinced. I don't want to say anything more. But this will be sufficient. You will see that all other combinations vanish. Trivial. Play with it a little bit now that you are told that. You don't have to study it. You don't care how the current. You can just study a little bit with this simple group theory and make sure that you are convinced that all the anomalies cancel with this thing, as long as the charge is off. So when I told you that we needed a Chan-Hong to understand flavor of conservation, that was not really a good argument. That was a lousy argument from logical. This is how Glacio, Ilopoulos, and Mayani wrote it up, because they didn't understand anything about the anomalies. They didn't even know that the theory was renormalizable. They had no idea at that time. This was 69, in 71 comes at Hof, so in the early 70s people slowly learned what standard model meant. Now we know that Chan-Hong had to exist. There will be no anomaly cancellation. You have to have a complete doublet here. So if I write mu prime mu and S, there will be no anomaly cancellation unless there is Chan-Hong. Simple. And yet, okay, why, for example, it leaves me unhappy at the end? Because I can tell you, look, I found a reason for charge quantization. I'm a genius, I've done something great. But then you ask me, what is your prediction associated with your... I can't make a prediction. I cannot tell you when you find new particles, they're always going to have the thing. I cannot tell you anything regarding possible quantum states. And I have no other consequence. I'm not saying, look, there is a new type of particle, there is something new. I don't have that. I have associated charge quantization to nothing except to my inability to formulate QED unless, all I said, it won't work unless, so it's not the thing what we love about physical theories making, explaining, giving you deeper understanding. We love these deeper understandings when there is an associated prediction which has nothing to do with the thing you wanted to understand, and it has to be there. So I will move unless you ask me to magnetic monopoles. You wanted to hear about magnetic monopoles, so. And I will try to give you a complete picture. I didn't talk about magnetic monopoles for a while, so I had to rethink what selection to make. It's an extraordinarily rich subject, so I'll try to focus on the essence.
This
Yes.
same diagram with gluons. If there is a strong...
Well, the gluons, you don't have to worry about gluons because there is no gamma 5 there.
if
Left is equal to right. When left is equal to right, you can separate left. So left will go as 1 plus gamma 5. And there will be a current. But remember, right goes as 1 minus gamma 5. So there will be a cancellation. Or better to say, there is no gamma 5 in the gluons. There is simply never gamma 5.
okay, so
Gluons don't see gamma 5.
our gauge theory, if it is left-right symmetric, then we
It's
have-
automatically anomaly free.
Okay, the anomaly we talked about strong.
Doesn't matter what anomaly. Doesn't matter what.
What that anomaly was?
When I talked about before, it was a strong QCD anomaly because I looked at some global current.
Yeah.
I didn't speak of the gauge current. There, I had an external gamma 5, imagining. If there is a set, then I took a symmetry, remember? Q going into e to the I, alpha gamma 5 Q. This is not a gauge symmetry of the standard model.
This is the flavor global symmetry.
No, this is something I imagined. It's not a symmetry because quarks are massless. I said, I can look at the massless quark limit, in which case I would have that symmetry, and the Lagrangian will be invariant, and I learned that even if quarks are massless, the action is not invariant. Lagrangian is not invariant because the associated current has an anomaly. So this can be any global symmetry, vary a number. Okay, I can as well say it here. Notice that the baryon current will have the anomaly in the standard model. Let's just say, look at this diagram. And take here the baryon number current. Just take the baryon number charge to see what is happening, okay? So you have two contributions. You have up quark. Take this to be W, the charge current, just to see what is going on. One of the combination of my generator. That goes with T plus and T minus. So, up, this becomes down in the up. What is the baryon number of up quark? 1/3. So this diagram contributes 1/3 times some coefficient C. Okay? I don't know how to compute it. Actually, we know there are some formulas, but I don't have to worry about that. Then there is also down quark. I can put outside down quark. right? I can now have a diagram with a down quark, which becomes an up quark. I will get 1/3 times C. I forgot to say there are 3 colors, so as well, let's put these 3 colors. This is the contribution of the W diagrams. There is an SU2, there will be no, I cannot put gluons here, I won't get an anomaly because there is no gamma phi. Here there is manifestly gamma phi, only left-handed, so I should have been very clear. Only left-handed guy is here. Notice I have a gamma phi interaction. So baryon number has an anomaly. Notice, let's check the lepton number. So what is the contribution here? The anomaly is 2C, whatever C is. Let's look at the lepton number, the same diagram. I can have here electron, you agree, becoming a neutrino and electron. What is the lepton number of the electron? So this is baryon number anomaly. The lepton number anomaly, it's 1 times C, this diagram, no color. But I can also put neutrino in the loop. That will also be 1C. So notice that the lepton number is 2C. There is a non-vanishing anomaly. Actually, proton is not stable even in the standard model. What I told you was a lie. And remember I said a number of times that I will tell you the truth and nothing but the truth. That's not easy. Okay, I'm not going to tell you the whole truth ever. Okay, I can't. I don't know the whole truth, of course, you can tell me. But I cannot tell you even what I know. Sometimes now I can say the baryon number is violated. Actually, proton does decay. And Hooft found a way of estimating, if you wish, to some degree even computing the thing. And you find out that the decay rate for proton decay, there is an exponential suppression. Times some scale. Put whatever you want, and proton, I don't care. Put the largest possible scale of the weak interaction, which is for fun. This is 0. Right? You see that this is 0. No? This is exponential suppressed. You remember that the whole thing worked. The anomaly is meaningful only because there are some kind of instantons. They have to do with something that happens in the infinity. Remember, it's not enough to have an anomaly. Then you needed these classical solutions, okay? These are nothing you get in perturbation theory. This is some incredible thing that had to do with the topology of the gauge fields, the infinity, and so on. The manifestation of the things that you get, things that you never get in perturbation theory. Look what a strange singularity, okay? In perturbation theory, you will never know that proton is. We, of course, don't care because you, from here, please put the proton lifetime is bigger than 10 to the 130 years. Notice another interesting thing. That look at B minus L. It's anomaly free. I don't care what C is. A lazy man's approach. B minus L is anomaly free. It's an incredible accident in the standard model. You can ask me why. Now, of course, I can give you an answer. Remember, I gave you a left-right symmetric theory. In a left-right symmetric theory, we found out that Q is T3L plus T3R plus B minus L over 2, we found out. And that's a gauge thing, it has to be anomaly free. And it is anomaly free. Actually there could be even a right-handed anomaly, so there is a right-handed neutrino, okay? You can understand from that point of view. But this is just a side remark, okay? You don't have to know this, a side remark. Maybe I should have done better by not making it. Let's just stick to the... So we can recapitulate. We don't worry about global anomalies. They are welcome, in a sense. It's really a pity that proton lives so long. It would have been beautiful that the standard model itself, because it's calculable to some degree. This really is a non-trivial disinstator calculation. The HOF managed to do that. This is mind-boggling. This was happening immediately. These were years in which every year there would be this magical new paper at HOF that we couldn't, it looked, someone said, I think Roger Dashan, they speak of great physics in Europe. He said, yeah, there is a great group at CERN, there are 20 theories. There is a better group in Utrecht, okay? That was at HOF. I will now mention what Helske did, okay, which is even more beautiful, okay? The number is too small. You would also make a prediction. You would say proton decays by such a way that B minus L is conserved. So for example, okay, let's see what it means. This you may appreciate. Whenever I have a B minus L conserving theory, then proton can decay into what? Let's try. Can it decay into pion plus a positron? This conserves charge. What about B minus L here? Is 1. So I'm writing B minus L. And here is 1. So this is allowed. Agree? Right? E plus has L minus 1, minus 1 is plus 1. B minus L is conserved. This is allowed. Okay, can neutron decay into, what could neutron decay?
How can you write it like at the quark cliff?
Sorry?
Can you write the first diagram at the quark cliff?
Which diagram?
The proton decay to the...
Well, I don't know the diagram here.
You shouldn't care about it, or...
How can I even imagine a diagram? I don't know what's causing it. There are some crazy instances, there is something strange happening, this anomaly. It's not that I have some new gauge boson or something, I have no perturbative interaction. I have no, I draw diagrams. Diagrams mean that there is a perturbative interaction and there is a well-defined tree-level result. Here there is no tree-level even. Notice what a strange situation we have. It is, well, you could have told me, well, it's obvious that it has nothing to do with perturbation theory. Perturbation theory means we have a tree level and then small corrections. Here we have a 0 at the tree level with whatever correction is then infinitely large. It's purely quantum, okay? So I can draw the diagram. That's why if I can draw the diagram, I can tell you what happens. If you give me some theory with some new gauge boson, I'll be able to tell you whether or not it conserves B minus L or whatever. Just give me those gauge bosons. Here is the other way around. All I know that B minus L doesn't have an anomaly. If it doesn't have an anomaly, it cannot be broken. So neutron, what could neutron decay? Let's see. Pi minus, okay. Plus E plus. That's okay, you agree. Right? I think it's correct what Emilio said. You agree? This conserves charge, conserves fermion number. We are conserving fermion number. Okay, with this anomaly we are not transforming fermions into bosons, okay? There is nothing crazy happening here. Okay, can neutron decay into pi plus electron? Would this be allowed? No. So you're making a prediction. See how beautiful it is. It's a pity that the lifetime is so wrong. You will tell experimentalists, if you find this, it's not coming from what I'm telling you, okay? There is something else. There is a new gauge interaction. And now we know by the, well, of course. It's irrelevant then to the 30 years, okay. 130 years, right? It's more or less, I remember roughly, I can dig up a more precise number, maybe there was 128, who cares? I guess I don't want to say anything else on this.
Were ununifying theories were developed before or after realizing this stuff?
The grand unification actually came a little earlier. The true understanding, this sort of was pushed to 1976. The early ideas of grand unification, 73, 74, Patti and Salam started the ideas of quark-lepton unification, which then immediately is followed by George Iglesias' SU5 paper, which is fully grand unified, but even Patti Salam were there, okay, with their quark-lepton. So we're talking about 73, 74, a couple of years before. So everybody got very excited. You can imagine proton was supposed to decay. Then there was even more excitement finding out that this would happen in the standard model, but then it lived very... Well, your first feeling was that it's going to be, even without it, there should be some kind of strange singularity which indicates that it's not perturbative. There is a way of understanding it that I don't want to now... no, this is one of the things I can't say. But when we finish, when we meet last time, I'll give you some stuff to read if you decide to keep reading. There are beautiful lecture notes by Coleman, who talks about, he shows that these such processes, okay, I can as well say, they have to do with what happens here is some kind of tunneling in field theory. This is really a tunneling phenomenon. You should always suspect that there is something like tunneling when you get exponential thing. Remember how tunneling goes? The WKB, there is this exponential suppression. And that sort of makes you guess, and then he goes on and shows nicely, he developed a theory of tunneling in quantum field theory. And he shows that tunneling is proportional. No, I may say it later. We are having 2 lectures today, right? That's what we said. So we have 2, 1, 2, 1. That means I studied at 2:30. No, 2:15. No, it was not that. 2:15. So I still have. Let's do hour and 15 minutes, right? Because so I got 20 more minutes. Okay. I think we said enough. You think about it. You see if you can digest it. I can come back tomorrow.
So this result of lifetime proton is not, we cannot write it as a series in the coupling, right? So
No.
that's why we call it
No.
perturbative. So
That's
then
why we call it non-perturbative, or we could also say we call it non-perturbative because there is nothing at the tree level. The theory doesn't. Perturbative, it means that there is a result at the classical level already. At the tree level, that we call the classical level, sorry, tree level.
But in general, these non-perturbative effects results looks like this, like exponential.
They look like this. Non-perturbative result.
Yeah.
And that's why in QCD they are relevant. In QCD there is no suppression because alpha is not small. The same thing, in QCD alpha would be 4 pi. And this is 1. If QCD were to do this, whatever QCD does regarding anomaly, tunneling, call it whatever word, is there. Okay? We don't maybe know how to compute it, but we expect the effect to be important.
Have they found any non-perturbative
Yes,
phenomena?
I'll talk about it probably when I come to the strong CP problem. QCD plays a fundamental role in the axion case. It gives a Goldstone boson a mass, and that mass is not. You would expect if anything like anomaly gives a mass to the Goldstone boson, it's going to be 10 to the minus whatever. I think e to the, let's see what it is. I said that it's, let's see how small it is. This is e to the minus, alpha is 1/30, so it's e to the minus 120. This is small. This is 0. talking of your zero, how in the world you distinguish, you know, when you appreciate the zero? How would you tell the experimentalist it's really zero and not, whatever? So this would be irrelevant. Any weak anomaly is completely irrelevant. But the QCD anomaly may be fundamentally maybe as strong as anything.
When alpha omega, when the coupling start to be higher, it will be none
Sure.
So.
Sure, the coupling, the thing is, however, remember that the SU2 coupling is asymptotically free, so it's not growing, it's getting smaller.
So is it that if we have the temperature of the universe really low or small?
Well, the temperature is there was a debate what happens at high temperature. And to a good degree, some years ago I wrote a paper in which I studied symmetry breaking at high temperature. We wrote the paper with Mohapatra, and we said the temperature should be like energy. So we did the usual running, and then some experts criticized us severely, and then some other experts criticized them. And then some experts criticized these experts, and then more experts. And then finally the prevailing view that it's like, I stop following, okay? I don't get involved in this nitty-gritty of... But I think now that you should think of it as energy is fairly well. So again, as you go down, back, what am I talking about? When the universe was young and it was hot, couplings should have been smaller, if anything. There could have been other effects.
No, but smaller coupling being...
Smaller effect? E to the minus 4 pi over...
So, it means that proton doesn't decay,
Whatever other thing you find, whatever you have, the smaller the coupling, the less relevant is the effect.
But I mean, from the formula of the decay rate, if we have
well, it's here. As alpha gets smaller, it gets weaker. I need alpha to become stronger. So I would need to reverse this. And it may happen tomorrow. After all, do I know new physics? This is a picture. When I wrote this picture, I imagined that the world is the way I see it today. And every time we thought that the world was the way we saw it, some other people looking back at it would say, why in the world would they say that they had to keep looking like that?
No, I mean at low temperatures, you're expecting with this behavior of the coupling constant, you're expecting the proton to decay faster, right? From the...
This is at low temperature. This is my electroweak coupling. I'm doing physics at low temperatures. This is low temperature. This is low temperature. I know it feels hot today, but this temperature is very low. The temperature at LHC, the temperature here is very low. It's 0, basically. You know what the temperature of 20, 30, 40 Celsius. We can go now to... I'm a lover of heat. I'm never hot. So I can say this with some assurance. Remember, the temperature is 0.
Okay, so it's calculated at when the coupling is...
Oh, we just take temperature equals 0. The field theory is formulated at 0 temperature. We never include the temperature. We don't have many particles that are in some kind of equilibrium. The temperature is too low to establish the equilibrium.
But how we calculate decay rate when we have the coupling non-repaired?
We calculate, we measure alpha, we do the scattering, we measure alpha. We know how to calculate, we use Feynman rules. I know you're asking something, I can't help you. But
the formula that we write for the proton decay rate, how it has been calculated, or why it should be like this?
This is electroweak coupling constant. The one is coming from the same electroweak physics as the one that I can compute other things.
Is U2 running this or like this? How?
It goes down.
Like
this is the running with relevant energies. You start running at energies which are relevant. You cannot draw this picture at 0 energies. Forget it. When I draw this picture, I typically draw for you at high energies. I start with MW and start running. Just to remind you, I thought you knew, how hot is MW? Everything in particle physics is infinitely large for practical world. I thought we decided that electron volt is 10 to the 4 Kelvin. So GeV is 10 to the 13 Kelvin, right? So MW is 10 to the 15 Kelvin. That's why I'm saying it's very cold today in particle physics units. 10 to the minus 15. Think of temperature in particle physics units and you will be freezing to death. These guys, I don't know how they take it, electrons, those guys. Sorry.
So then, for very cold temperatures, why don't this decay effect enhances? Like
No, this is the result. The field theory that you have formulated at zero temperature. Then you have to study what happens at high temperature. The field theory, you never introduce any temperature. Where is the temperature? I don't understand.
what's the value of alpha on alpha W at zero temperature?
Well, everything was formulated at zero temperature, of course. There was never temperature. I never introduced temperature. That means that I assumed the temperature was zero. I can justify it now that when I do experiments, I don't even have to really cool the system very much. I can do the scattering of electrons here. It will be practically zero. You agree, the temperature. Kelvin is 10 to the minus 15. Well, 100 Kelvin is 10 to the minus 13. So 10 to the minus 12. In other words, the temperature is 12 orders of magnitude more than the energy I'm talking about. Therefore, for me, it's zero. Well, I'm ignoring the effect. Everything I do in the standard model is at best at 1 in 1,000 precision. Okay, it's a high precision theory, but not to the 12 decimal points. So the field theory is formulated at zero temperature. There is this. That's why it's sort of complicated to understand what do you really mean by temperature. What? I remember when. In the early 70s, Kirchnitz and Linde started it, and then Jakiv and Dolan and Weinberg completed this picture. What will happen to the standard model at very high temperature? I remember Jakiv came to give a talk. This was City College of New York, where I was doing my PhD, and he's talking about temperature. We are also puzzled. And you know, should I ask or should I not ask? The same thing that you have. So remember Sakita, who was a distinguished physicist, he says, what do you mean by temperature? So Jakiv takes the jacket off. He says, you know this, now I feel hot, so I'm taking it. He was joking, he meant really temperature, but it's not easy to establish the connection between the first, thermodynamics, statistical physics is already a profound thing, right? Then I have to establish it in the field theory for you to see. So I need a collective behavior of many particles. This is not what we do. At experiments, we take one or two particles colliding with each other. Temperature is a relevant concept. Temperature means that you have many, many particles which are sufficiently strongly interacting to create equilibrium, sufficiently weakly interacting so that you can ignore that interaction. Now think of that as ideal gas once the equilibrium is established. And that usually means many, many particles, right, in a box. So it's a completely different kind of physics. If we want to do high temperature, we have to imagine this thing that we create processes with many particles. And then I have to see what the temperature is in relation to this. So I don't want to talk about it. I mean, we never introduce it.
Yes, but I'm confused now because.
I can see that. Sorry.
Because we said that we can do the perturbative calculation for proton-proton collision because like in galaxy you have asymptotic Freudian
energy is big, right?
Or the coupling of the QCD.
Right, it's small, right.
It's small, but now we're saying we have energies that it's high, but it's related to the temperature now.
Well, alpha weak is 1/30, roughly, at LHC, even smaller.
But
so it's small.
But you said no, the temperature is not that you have just particles colliding.
Temperature zero. Temperature zero. This is the field theory studied was a zero temperature. This is a number of zero temperature. Why are you bugged about temperature? There is no temperature.
Okay.
How can there be a temperature where a proton hits a proton? What would the temperature be? Proton temperature is a concept when there are many, many species that actually interact with each other continuously.
You just speak about energies with how the coupling can run with energies, not with the temperature.
Yeah, of course.
Okay.
So when you want to decide how they move with temperature, it becomes a sophisticated subject that I said I stopped following because it became too technical for me. So here the analogy, is a tricky one because Anyway, the physics at high temperature changes completely, right? At high temperatures, concepts break down and everything, but
And so in the energy scale, I will limit it from down for proton to make alpha W go higher and higher, such that this decay becomes relevant.
this,
Yes. Like for proton, maybe we are bounded from below by the proton mass to make alpha big run up.
you mean why don't I run backwards?
Yes, that's what
Why don't I run weak interactions? Why? Tell me. Let's see. Anybody know?
Spontaneous breaking is, if we're talking about electrolyte, spontaneous breaking will come in.
At some scale. Before that, there are no. What happens when you are at low energies? There is no gauge theory. That's Fermi theory.
It's broken.
It's crazy to talk about gauge theories. I mean, Fermi was not completely stupid. I want you to understand that. So Fermi knew that there could have been a double boson, the analogous to the. He says that, by the way. He writes this, and he says, "I don't want to talk." This, of course, could be equivalent to some fundamental interaction with some gauge coupling that I introduced, but it's a useless language because the guys don't exist at lower energies. There are no W boson. This is a much better theory to work with.
Okay, but this effect is through instantaneous, so is it still there after we broke SU2 spontaneously?
I wouldn't talk about that. I would be scared to talk about it, but maybe you can, yes. Yes. That's why I put NW there. Now you're asking me a good question. Could I even use that language? Maybe I can still use language. Maybe the scale of, the instantaneous, when you look at the QCD, instantaneous have all sizes if you wish. There are some classical solutions which have all sizes. Otherwise, solutions, I'll introduce today. By the way, to speak about instantaneous, the order should be what I will do now. So it's good that you wanted to learn about monopoles. I will teach you about classical solutions in field theory, and then you will see that they have their sizes. In their instantaneous, it turns out that all of the sizes contribute, okay, because QCD is not broken. In electro-V scale, this will cut off so probably then you say, at this point I cannot even, when I go below MW, I don't want to even talk about that. I never studied it in detail to speak with authority. But let me think about it. Remember that the running is very little. There is no running. Think about that, okay? It should be called crawling. This terrible language is, okay, it's confusing us very often. The effects are so small. It's irrelevant that this changes a little bit. You have to go to huge energies to see appreciable change. Huge energies. Unimaginable energies that made us go to grand unification, which may be insane. My generation spent a lot of time, people went to strings, so that's orders of magnitude more insane. But one insanity breeds another insanity, When you go crazy, you go crazy. I couldn't get, I got excited in grand unification. Looking back, maybe it's crazy to speak about what happens 13 orders of magnitude above the energies where you do experiment. But it was irresistible. So you know how life is. Once you sin, you. Oh, so there will be no time to. So let me tell you what the plan is today. I'd like to talk to you about monopoles, magnetic monopoles. You will see something far more beautiful than the anomaly cancellation. We will see how the existence of monopoles quantizes the charge. But I won't start now. So what I will teach you is show you this is Dirac work. As you imagine that there is one point monopole, point-like. And then we will try to understand the physics of that. And then I'd like to teach you, which is far more exciting, the work of Hoff and Polyakov, again at Hoff, to show that if you have gauge series with quantized charge, like SO3, SU2 we started with, or SU5, you actually predict magnetic monopoles. So I'd like to teach you both. And I'll send you some notes on mine, which are for your eyes only, something that 23 years ago was to be a book. I wrote some pages or something, a book, and it's still badly written.